You turn on the shower and expect steady hot water. One heater keeps a big bath of water hot all day. The other keeps none at all and heats water in the 2 or 3 seconds it rushes past. How does that even work? Your shower asks for water at about 120 degrees. It also changes its mind. One shower, then two showers, then maybe a sink. The heater has to keep up as the flow rises and falls. That is the first job. Seasons make the job harder. In winter, the water coming in can be 45 degrees. In summer, it might be 70. You want the same set point either way. The heater must do much more work in winter for the same shower. Your pipes are a tiny reservoir. The water sitting in the lines is why you wait. It is room temperature until the hot water from the heater reaches you. Both types face that same delay. There are two main approaches: a big insulated tank that stays hot and ready, or a compact box that stays off, then fires only when you open a tap. Both can work well. They solve the same problem in very different ways. A storage tank looks simple, but it is not just a barrel. Inside is 40 to 50 gallons, kept around 120 degrees. A thermostat tells the burner or elements when to heat. Thick insulation slows the heat that leaks away. Cold water comes in through a dip tube. It pushes the cold to the bottom. That protects the hot layer on top. The fancy name is thermal stratification. It means you draw the hottest water first. A metal rod inside this tank quietly gives itself up. It is called an anode. It corrodes instead of the steel tank. That is why your tank lasts years. When the anode is used up, the tank starts to rust. Gas models have a flue through the center. A baffle in the flue helps peel off heat into the water. Electric tanks use one or two elements. Same goal. Get heat into the water and keep most of it there. One more part is not optional: a temperature and pressure relief valve. It opens if the tank ever gets too hot or too high in pressure. Never cap it. It is a safety vent, not a decoration. When you open a hot tap, the top layer in the tank goes first. That is why a tank has a strong burst at the start. The first hour rating mixes stored hot water and what the burner can add in that hour. A 40-gallon gas tank can give the feel of 60 to 90 gallons in that window. Take a 2.5-gallon per minute shower. In many homes, you can drain the usable hot portion in 10 to 15 minutes. It depends on how cold the inlet is and how much cold you mix at the shower. There is a cost for always being ready. Heat slips out while the tank sits. Those are standby losses. Typical gas storage units lose about 30 to 40% over the test cycle. Electric storage tanks do better because there is no flue. The test number for this is called UEF. Rules changed in 2015. Tanks got thicker insulation. The test method also changed in 2017. The new number is UEF. It compares heaters under a standard set of draws. Storing warm water has a health risk if you do it wrong. Legionella bacteria like warm, stale water. Best practice is to store hotter, around 140 degrees. Then use mixing valves to deliver about 120 degrees at the tap. That gives safety and more usable hot water. Now the other way. A tankless heater waits for flow. A small sensor feels water move. Most need around 0.3 to 0.5 gallons per minute to wake up. Once it wakes, a fan spins and an igniter lights the burner. A modulating gas valve feeds only as much flame as you need. Think of a car pedal for fire. Light touch at a trickle, full push when 2 showers run. The heat moves through a dense copper or stainless coil. Water rushes through those tight passages. The coil has a lot of surface area, so it soaks heat into the water fast. A control board watches sensors and chases your set point in real time. You crack a second tap. It opens the gas a bit more. You close the tap. It backs off. It does this every second you run water. The burners are not small. Many are 150 to 199,000 BTU per hour. That is like a small furnace pointed at water. It has to be. The water only stays inside for a few seconds. Here's what that power means for flow. A 199,000 unit can hold around 4.5 to 5.5 gallons per minute at a 70-degree rise. Cut the rise to 35 degrees, and it may do around 9 to 11 gallons per minute. Brand charts vary, but the idea holds. High places change the math. Thin air means less oxygen. Many models lose about 4% of capacity for every 1,000 feet up. At 5,000 feet, that is roughly a 20% cut. Your max gallons per minute goes down. Try a winter morning test. The inlet is 45 degrees. Two showers use 2 gallons per minute each. That is 4 gallons per minute total. A top tankless can hold around 4 to 4.5 gallons per minute to 120 degrees at that rise. Add a small sink at half a gallon per minute, and it may hunt or cool. Someone needs to throttle back. There is also pressure drop inside the tankless. Water squeezes through a tight heat exchanger. Your fixtures might be rated for a flow you never see with the heater in line. The drop is normal. It is part of the design. Let us clear some quirks. People say tankless is instant. The heater fires fast, yes, but the weight you feel is almost always the water in the pipe run. Half-inch copper holds about 0.012 gallons per foot. A 60 to 100 foot run can be around 20 to 30 seconds at a normal shower flow. Tanks weight 2, same pipe. Another quirk has a funny name, the cold water sandwich. You open a tap for a moment, then shut it. Heat stays in the metal coil. When you open the tap again, you get a short hot burst from that stored heat. Then a brief cool while the burner relights. Then steady hot. One more limit is very low flow. Many tankless units will not fire below around 0.3 to 0.5 gallons per minute. A tiny trickle to rinse a brush may not turn it on. That is normal. The fix is to open the tap a bit more. If you want fast hot at a far sink, you need a loop. A demand recirculation pump moves hot water to the fixture when you push a button or when a sensor sees motion. That cuts wait time to a few seconds. It does add some standby losses back into the system. Now the efficiency picture. A non-condensing tankless turns roughly 81 to 84% of the fuel into hot water under the test. A condensing unit can do around 90 to 96%. Typical gas storage sits around 60 to 68%. Electric storage sits around 90 to 93% under the test. Condensing units run the exhaust cool, often cool enough for plastic vent pipe. But that heat goes somewhere. Water in the exhaust condenses and drips out. The liquid is acidic, often between pH 3 and 5. You need a drain and usually a small neutralizer. At full fire, you can make close to a gallon per hour. On-demand heat means very low standby loss. If you live alone or travel a lot, that helps. You only burn when you run water. There is hidden stuff in the walls to make tankless work well. Gas tankless often need larger gas lines than a small tank. Think 3/4 inch or even 1 inch. That is a common retrofit surprise. Venting also changes. A non-condensing tankless needs special stainless vent pipe. A condensing one can use plastic and needs a drain for the condensate. The route matters and local code rules here. Electric whole home tankless looks simple on the wall. The current it needs is not simple. Many draw 18 to 36 kilowatts at 240 volts. That can be 75 to 150 amps. Older panels may not have that to spare. Here's a real number. A 27 kilowatt unit draws about 112 amps. Many use 3 double pole breakers at 40 amps each. Some homes need a service upgrade to feed that. Water quality matters too. Hard water builds scale inside the heat exchanger. Above about 7 to 10 grains per gallon, you start to see it. Flow drops. Outlet temperature falls. The unit may start to hunt. Many makers suggest yearly descaling in hard water areas. A tech closes 2 service valves. They connect a small pump and a bucket of vinegar or cleaner. They circulate for about 45 minutes. Flow and temperature control snap back. Recirculation loops can pair with tankless too. They cut the weight at far taps, but they bring back some standby loss. A smart middle ground is demand-controlled recirculation. It runs only when you ask. Safety stays front and center, whatever you pick. Anti-scald mixing valves protect you at the tap. They also let tanks store at 140 degrees for better safety against bacteria and a stronger first hour. That relief valve on a tank exists for a reason. If the tank ever overheats or pressure spikes, it vents water on purpose. Never plug it, never cap it, give it a clear drain path. Tankless units also have range limits. Many start at around 15 to 20,000 BTU per hour. Premium models can modulate from that low number up to 199,000. That wide range makes steady temperatures easier. So which fits where? In a small apartment with 1 shower, either works. A tankless saves floor space and standby loss. Check that your gas or electric service can feed it. In a busy home with 2 showers and a sink in winter, a top gas tankless can hold around 4 to 4.5 gallons per minute at a 75 to 80 degree rise. Go past that and it will back off flow or the water will cool. A tank can start strong, then fade after 10 to 15 minutes. If your family likes long showers, a tank will not keep up forever. It gives a strong start, then the outlet temperature slopes down as you run. A tankless does not run out. It is capped by maximum gallons per minute at your rise. If your kitchen is far from the heater, both wait on pipe volume. A demand recirc button can give fast hot with either system. It is a comfort add-on, not a heater type. A fun bit of history shows how small parts matter. In the 1990s, some dip tubes and tanks broke down. Little plastic bits clogged fixtures. Hot water delivery dropped. A cheap tube changed the whole system. Here is the mental model I use. A tank is stored heat plus recovery. A tankless is real-time sensing and modulation. The clever part is not only burning fuel, it is how the system notices what you do and shapes the water while you use it. The scale of it is wild. To lift cold water to shower temperature in 2 or 3 seconds, you need a furnace-sized burner aimed at a heat exchanger the size of your hands. It does that quietly, every day. Pick based on your pipes, your climate, and your peak flows, not just the logo on the box. If this kind of clear, inside-the-walls engineering is your thing, subscribe and poke around the channel. Drop a like if this helped you size your next heater. We have more on power, plumbing, and the hidden gear that makes homes work. See you next time.